problems, you will find them in the questions that we have solved before. Thanks for your wishes, Tanshu. So you will find everything you need to solve friction and Newton's laws based questions within the discussions that we've had in class. But then at the same time, as you practice more questions, you can get stuck with something or might require my help with something. So that's why we will keep some time aside in the next couple of weeks in one lecture or the other for discussion of the same. Okay, so your aim should be to complete the problems from at least exercise 1 and 2 of your module, as well as from HC Verma completely. And of course, now we'll gradually have to start working on the assignments from work, power, energy also. So let's begin with this next section, work, power, and energy. So this is another key chapter in mechanics. Okay. And the ideas in this chapter, which are mainly to do with the relationship between work done by a force and energy of a system, different types of mechanical energy of a system, like kinetic energy and potential energy. So the main idea in the chapter, or in this in this analysis, the main idea is to again be able to solve mechanical systems and to be able to represent them with equations. But this time the equations are going to be scalar equations, because the quantities we are dealing with are going to be things like power, work done by a force, kinetic energy of a system, potential energy of a system, which are all scalar quantities. Whereas in the previous chapters, that the analysis we saw of mechanical systems were through vector relations, that is the relationship between the net force or the combination of all the forces acting on a system and the acceleration, or rather on a body and its acceleration, or its momentum or rate of change of momentum. So all these were vector quantities, whereas now we will look at a scalar analysis involving scalar quantities like work done and kinetic energy and potential energy, etc. So it's another interesting way of looking at mechanical systems and solving mechanical systems, representing them by equations. So and we will see that this, because it's a scalar analysis, certain types of systems that are very difficult to analyze by Newton's laws of motion, or free body diagrams and applications of all that, they are quite easily solved by using the work energy method. Okay, some types of situations where the mathematical complexity of application of Newton's second law becomes very tough because of the vector nature. But we will see that in certain cases, the application of the scalar principles of work and energy, and the relationship between work done by forces and the mechanical energy of the system, that analysis is much easier. So there are certain types of mechanical problems or mechanical situations which are such that they are very easy to solve using this compared to Newton's laws. Vice versa also holds true. There might be certain situations where application of Newton's laws is easier, but generally it's the other way around. If we are struggling with the application of Newton's laws because of the complexity of the vector equations, then generally speaking, it might be a good idea to look at the application of work energy in the same system and see if the scalar equations gives us an easier solution. So anyhow, let's start with the basics of it first. So the first definition that we will learn over here, the absolute basic, is the concept of work. And this is very different from our everyday meaning of work, or the layman's uh, definition of the quantity work. This is mechanical work. Okay, so what we are defining here is in context of mechanical work done, or how the application of work in mechanics. So work, or we can also call this work done, is in context of, it is always work done by a force, or it can be net work done by a combination of forces, but essentially it is a quantity which is connected with force. Okay, so let's understand the definition of this. Now, as you might have studied in 9th, 10th earlier, there's a general type of definition that work done is force multiplied by displacement in the direction of force, something like that. But here we give it a more mathematical kind of definition, a more specific kind of definition. So we will actually look at the definition of work done in two categories. Okay, the first category is when we are talking about the work done by a constant force. So if the force we are dealing with is such that neither its magnitude changes nor its direction changes while it is acting, or while it is creating some change in the system, then there is one way to define the work done, and we look at that. Okay. So work done by a constant force F. Okay. And by constant, we mean that both magnitude and direction of the force should be constant. So both magnitude as well as the direction should be constant. So that is the meaning of a constant force. If only the magnitude is constant but the direction is changing continuously, then we cannot call such a force as a constant force, because force by definition is a vector quantity, and for a vector to be constant, both the properties of the vector, the magnitude as well as the direction, should be constant. Okay, so work done by a constant force through a displacement S. Let's see how we define this. So this is defined in one single formula as far as the mathematical definition is concerned. It's just the dot product or the scalar product of force with displacement. So it is just defined as work done equals to the scalar product of force and displacement. So we can also write it as W is equal to Fs cos theta, where theta is the angle between the force vector and the displacement vector. Okay, so you can start by noting down this definition. Yes, Hitanshu, that's correct. Okay. So immediately in the definition, you can see one thing, that it is a scalar quantity, because the scalar product of two gives you a scalar quantity. Work done is a scalar, okay, and can be positive if theta is acute, okay, can be 0 if theta is 90 degrees, and then again it can be negative also if theta is obtuse. Okay. So depending on the angle between the displacement and the force, which is constant, and the work done by which we are calculating, the scalar work done quantity can be a positive scalar, it can be 0, it can be a negative scalar. Okay, now let's look at the next thing, that as far as unit is concerned, the SI unit of work, I'm sure you're aware of this, okay, is called Joule. It's named after the physicist Joule. Joule heating and thermodynamics, a lot of work was done by the physicist called Joule. So anyway, the unit of work is Joule, and in SI system, and 1 Joule is equivalent to 1 Newton meter, okay, or 1 kilogram meter square per second square. So you can understand the dimensionality of the units in the equation only, Fs cos theta. So F will have the unit of Newton, S will have the unit of meters, whereas cos theta is a dimensionless quantity. It's a unitless quantity. It's just a mathematical ratio. All right. So hence, the unit in SI system 1 Joule will be equivalent to 1 unit of force multiplied by 1 unit of displacement in SI system, whereas in CGS system, centimeter gram second system, the unit will be, so it is specifically called ergs, okay, ERG, erg, and as you can see, 1 erg would be equivalent to the unit of force in CGS, which is dyne, multiplied by the unit of displacement, which would be centimeters. Okay. So 1 erg would be equivalent to 1 dyne centimeter, or 1 gram centimeter square per second square. Okay. And therefore, from this, you can also see the conversion, that 1 Joule is equivalent to 10 raised power 7 ergs. Okay. Or inverse of that, that 1 erg would be equivalent to 10 raised power minus 7 joules. And joules generally we write in short form with capital J. So that is as far as the unit is concerned. Now the most important thing over here, which we have not talked about till now, is when we are doing the dot product of force and displacement, what exactly is the displacement we are talking about? Whose displacement? You have to understand that in detail. So for the definition, work done equal to F dot S. S is fine, it's displacement, but the question is, what displacement do we have to measure? Or you have to note, okay, no problems. Let's finish this off first. Okay, good. Okay, so now let's come to this very important point. So pay attention here. Okay. So यहाँ पे S exactly क्या है? मतलब obviously it's a displacement, but the important thing is what displacement do we measure? So S, the proper definition of S over here is that it is the displacement of the point at which the force is acting. So that point is called the point of application. So just note this down first. It will seem complicated. I'll explain with examples, then you'll understand easily what it means. So it's the displacement of the point of application of the force F, okay, during the time for which the work done is calculated. Okay, so for example, I want to say that calculate the work done by the force for this interval of time, for the next 30 minutes or for the next 1 minute or whatever. So we have to understand that what is the displacement of the point at which we are applying the force during that time interval for the next 30 minutes or that next 1 minute or whatever, and then take the dot product of the force with that, provided of course the force is constant. It should not be changing during that time interval. Okay, so let's understand this in more detail. So now this statement, let's look at sort of how we would apply or implement this statement. So if F is acting on a particle, suppose, then it's the simplest case. We don't need to worry about things too much. Okay, in that case, then S is the same thing, is the same as the displacement of the particle itself, because the particle is a point mass, no? So the force is acting on that point only where the particle is located. So whatever the displacement of the point on which the force is acting, or the point of application, that is the same as the displacement of the particle that we are talking about on which the force is acting. So then S is the same thing as the displacement of the particle. Okay, so let me explain this with an example. So suppose this is a particle P, okay, and particle P moves from, let's say, the position A to the position B. So it moves from the position A, which was somewhere over here, let's say, via some kind of complicated path like this, it moves to the new position B in a certain interval of time. And while it is moving continuously, there is a constant force acting on it, which we can, let's say, denote with this vector. So there is a certain force which is continuously acting on the particle. Let's say that force is this. So when it's here also, the force is this. When by the time it reaches also, so everywhere there's a constant, or there's a constant force vector F that is acting on it. So you can see that the force is acting on the particle. So the point of application of the force is the same thing as the particle itself, because it's acting on a point mass. A particle is nothing but a point mass. So there is no difference between the point of application and the point mass on which it's acting. Actually, they're one and the same point. So we just have to calculate this. This is the displacement of the particle from A to B. It doesn't matter what the path of the particle is. Okay, the path might be more complicated, like this path I've shown, but the displacement is just the vector joining the initial with the final position. So the work done. So the work done by that force F from A to B for that interval where the particle is going from A to B is simply this. It is the scalar product of this force vector, which you can see in the diagram, and this displacement vector, which you can see in the diagram. So this is the simplest situation. If we are talking about work done by a force acting on a particle, then we really don't have to worry about, okay, what is the point of application, what's happening to that, because the particle is only the point of application. Okay, so hope this point is clear. Make a note of this. Okay. Then I'll show you a situation where it's a little bit more complex than this. Point of application, Aryan, means that, see, a force is a vector quantity, no? So it always acts at a certain point. Understanding? Like I'm saying, let's say that this is a body on which I'm applying some force. So I could be applying that force over here. I could be applying that force over here. I could be applying that force over here. So whichever point at which the force vector is actually acting, that is called the point of application. Okay, now when we are talking about a particle and a force is acting on the particle, so there is no choice of point. No? The particle is a single point only. So whatever the point of application, that's the location of the particle only. Okay, yeah, Hitanju, I'm coming to all that. This is just one example. So if the force is acting on a particle, okay, then the displacement that we're talking about in the definition, W is equal to F dot S, that's the same thing as the displacement of the particle itself. Okay. Okay, just take down this example, Nitancho. There will be more examples and you'll understand the whole thing better with them. Now, next situation. Let's understand why something like this is happening. If force F acts on a rigid body, okay, like a solid block, okay, which is in translation type of motion. In kinematics, you would have studied that there is translation and then there is rotation. So translation or linear motion, okay, that kind of situation. So let's imagine this with a diagram. Okay. So imagine a physical situation like this, that you have some kind of a surface on which a block is being pushed. Okay. And this block is being pushed with some kind of a force, which is, let's say, represented by this vector. Okay. So a constant force F, okay, pushes this block from the initial position A to, after some time, the final position B. Let's say like this. Okay. And while this pushing is going on, this force is continuously acting on it. Continuously, the force is neither changing in magnitude nor changing in direction. Okay. So what is the point of application of the force over here? It is this point. So when we write in the definition, you know, that the dot product is of force with displacement, where displacement is what? It is the displacement of the point of application. So S over here will be the displacement of the point of application, which I have labeled with the symbol P over here for the force. So in this diagram, I will have to actually figure out that what is the displacement of this point P as the entire body is moving from A to B. So that is this vector. Okay. And you will see that because it is in linear motion, okay, so because in this case, okay, the rigid body is in linear motion, okay, or translation. S is again identical to the displacement of the center of mass. In mechanics, we denote the center of mass with the symbol Cm. So the displacement of that point of application is the same as the displacement of center of mass of the body. You can see that the body's center of mass is going from this position here to this position. Okay. So that's the same displacement as the above one, which is the displacement of the point of application. Why? Because the body is in which type of motion? It's in pure translation, or it's in linear motion. So the displacement of the center of mass is the same as the displacement of that point above, or any other point in the body. Okay. So this is also a simple situation for calculation of work done. And in this particular chapter in our mechanics, we will be applying the concept of work done only to these two situations which I've shown you. Either we are talking about work done by force acting on a particle, or the work done by force acting on a rigid body, but the rigid body is in this type of motion, linear motion, that is straight line motion. So the displacement we are talking about is nothing but the displacement of the center of mass of the rigid body, or that's the same thing as the displacement of the particle, or that's the same thing as the displacement of the point of application. However, in future chapters like rotational mechanics, like properties of matter and elasticity, there is a more specific point over there, which I will show you with a couple of more examples. And for that purpose only, I'm giving you the proper definition of displacement of point of application. Yes, fine. Even the shape is irregular, it does not matter. But if the motion is linear, then the point of application will have the same displacement as the center of mass. Okay. I can have an irregular shaped rigid body like this. Okay. So its center of mass is somewhere here. Now, if this is moving in such a way that it's not rotating, it's just going in linear motion like this. Whereas the force that is acting at this point. So again, you can see that the displacement of the center of mass will be the same thing as the displacement of the point of application. It will be the same as the displacement of the point where the force is being applied. So this above, description, it applies to this situation also. Where it will not apply is where there is rotation involved, which I will show you in the next example. When there is rotation of the rigid body involved, then the displacement of the point of application is not going to be identical to the displacement of the center of mass. So hope this point is clear, Rupesh. Very good. Okay. Just take this down. Then we will understand the next example with rotation involved, and it will become 100% clear to you. Okay, now let's understand the next example. Where we are talking about a force acting on a rigid body which is in rotational motion. Work done by force acting on a rigid body in rotation about a fixed axis. Now this is going to present a different situation. The moment you look at the example, you will understand. Achha, you have not written down? No problem. We'll come back to this example. Let's finish writing this down. Okay, so now let's imagine a situation. So here imagine something like this. You have like something that looks like a pendulum, a thin uniform rod which is hinged, or there's like a pin going through it, attached into a wall, so that pin acts like a hinge. Okay, so this is a rod which is having a hinge at one end, so it can rotate freely about that hinge. Okay, about this fixed hinge. That hinge is fixed to a wall or something. Okay, and now what we are doing is, let's say we are applying some external force which is constant again, but we are applying it to the bottom end of the rod. So the point of application of the force is this. So now you'll immediately understand what we are talking about when it comes to trying to understand the proper definition of displacement in the work done equation. So as this rod moves, it's not going to move in translation. It's not going to be a situation like this, that we are applying force like this and the body moves from here to here like this. This is not going to happen over here. Instead, what's going to happen is this. As we apply the force, the body will continuously rotate like this, in this kind of a motion. So the point of application will be describing a circle. The center of mass will be describing a circular path, but of different radii. So that's the important thing. So now, after some time, let's say the body has reached this position. So this is where it is at some time t1. This is where it was at t equal to 0. So in that time, how will we calculate the work done by this force? We'll have to calculate it as the dot product of this force vector with the displacement of the point of application of the force. So the displacement of the point of application of the force, you can see, is this vector now. Even though the path is circular, but displacement will be this now. So the path of that point is a circular path going from here to here. But this will be the displacement. Okay. So S is the displacement of the point of application of the force. Okay. Whereas in the same diagram, if you try to understand where the center of mass of the body has gone, the center of mass of the rod has not had the same kind of displacement. It had this kind of displacement. So they're not the same. They're parallel, definitely, but they're not the same. The center of mass has gone from here to here. So notice that in this particular case, because there's rotation involved, the displacement of the point of application is not equal to the displacement of the center of mass. And this happens because the body is rotating. So anytime there is rotation involved, this particular phenomena happens. So in such a situation, we have to be careful about the quantity S in the calculation of work done. So as I told you, this complication will not come right now in this chapter for us, but it will come for you later in the chapter of rotational mechanics. When you are applying the concept of work done in rotational mechanics chapter, you'll have to take care of this point, that whenever there's rotation involved, you have to be careful that what is the displacement of point of application, and not to mix it up with the displacement of center of mass. Okay. So this is an important point. So work done by the force F in the time interval 0 to t1, that will become F dot S. Okay, where we should be clear about what S is. Where S is this vector. the displacement of the point P, not the SCM, which is the displacement of the center of mass. Okay, people, so hope you're done with this example. Now let us look at a numerical example of calculation of work done. Okay, okay, no problem, Surukesh. Okay, so let's come to our first numerical example of calculation of work done next. Okay. So in this example, we have to just implement the formula that work done by a constant force is F dot S, which we have seen earlier. So let's imagine this situation that we have an inclined plane of 37-degree inclination and the coefficient of friction is 0.5. And now on that inclined plane, a block of a certain mass is sliding down from, let's say, this position A to this position B after some time. So mass of the block is given to us as 2.5 kilograms and acceleration due to gravity is 10 meters per second square. So we have to find the work done by each of the forces acting on the block, okay, for its displacement from A to B, okay, given that AB is a distance of, let us say, 20 meters. From the position A to the position B is a distance of 20 meters. Okay. This is a very simple problem. So all you have to do is first make the free body diagram, okay, and determine all forces acting. First step, okay, and then calculate work done by each of the forces by using this formula. Okay. Calculate W is equal to F dot S for each of the forces. Separately for each of the forces acting. So there's a bit of background knowledge of Newton's laws and friction you must have, okay, obviously to do a problem like this. But once you have determined the forces and their magnitude and direction and all that from the free body diagram application, next thing you have to do is apply the definition of work done, that is F dot S. Because all the forces you will find out here are constant forces. They are neither changing magnitude nor direction. Okay, so let's start up by looking at the free body diagram. So work done by which force, Ruxar? You have to specify each of the forces, huh? Whether it is the work done by weight or work done by the normal reaction force or the work done by the frictional force. So what are all the forces acting on it? You can see that the forces are mg, which is going to act vertically downwards, right? Then normal reaction force, which will act in this sort of direction, and frictional force, which will act in this sort of direction. So these are the various forces which are going to act on the body. Kinetic friction, N and mg. Okay, so let me come to that, Ruxel. Be careful of the algebraic sign. Remember what I told you, that if the angle is obtuse between displacement and, so the body is going to displace like this now. This will be the displacement vector, which has a magnitude of how much? The displacement has a magnitude of 20 meters. Okay. So as it goes from A to B, okay. Now the important thing of the angles. This angle here is theta, which is 37 degrees. So this angle here, this will become how much? This will become its complement. It will become 53 degrees. Okay. And the magnitude of mg you can see will be 25 newtons. Okay. The magnitude of normal reaction will be mg cos theta, so it will become 20 newtons. And kinetic friction, which is mu n, will become 10 newtons magnitude, right? So these are all the forces. Okay. Now for each of the forces we have to calculate work done. So you can see that work done by the weight, let's call that W by mg, that is going to be the dot product of the force mg with the displacement. So that in the diagram you can see will be mgs cos 53 degrees, because the angle between the weight vector and this you can see is 53 degrees. So mg is 25, this is 20, but cos 53 is how much? It is 3 by 5. Okay, so it will be plus 600 joules. So the work done by the weight of the body or the gravitational force acting on the body, that work done will be equal to 600 joules. Now similarly you calculate what is work done by normal reaction. Okay, and you calculate what is work done by friction finally. So work it out and tell me the answers quickly. Yes, Kunj, that is correct. Look, sir, what is the angle between normal reaction and displacement? Tell me what is the angle. You can see in the diagram now, beta. Normal reaction is acting perpendicular to the surface, na? And displacement is along the surface. So the angle between the normal reaction vector and the displacement vector is 90 degrees. Na? The 90-degree angle. So work done should be 0, na, beta? Should be 0. Because n is perpendicular to the displacement. Cos 90 is 0. Now similarly in the same diagram you can see that friction is acting in this direction. Kinetic friction is acting exactly at 180 degrees with respect to displacement. So work done by friction will in fact become a negative quantity. Okay. So that will become how much? That will become frictional force we had seen earlier was 10 newtons. So this will be minus 200 joules. Okay. This was 10 newtons. And the displacement's magnitude is 20 meters. Okay. So here we are using the fact that cos 180 degrees is minus 1. So hope the calculation is clear to all of you. Oh, this is 300. Yeah. Yeah, people, Kunj, thanks for pointing out. There is a calculation thing here. This should not be 600, this should be 300. This should be plus 300 joules. Please make this correction. Just do this calculation 25 into 20 into 3 by 5, it will give you 300. Yes, generally speaking, normal reaction will do 0 work ohm. But see, that's I'm saying in a situation like this. But there is another situation where in which normal reaction can do work. For example, I have this plate on which I've kept this block. Okay, and now this is going up. Okay, so the normal reaction acting on this block is going to create a displacement in the direction of the force. No? So here work done will by normal reaction will be a positive quantity. Okay, or if it was coming down, then the normal reaction would be doing negative work. But on a stationary surface, yes, work done by normal reaction will be 0. So we can't generalize the statement that every time the work done by normal reaction is 0. But yes, if an object is sliding down an inclined plane and the inclined plane is stationary, then definitely yes, we can say that every time the work done will be 0. Okay. Yeah, so people make sure that you put this correction in. This is not 600 joules, this is 300 joules. Yes, Kunj, the value is correct now. 300 joules is the answer you got also. Okay, very good. Okay, so 3 forces acting and we've calculated the work done by each of them. Okay, let's look at another example. And in this example, you will have to use a bit of your previous knowledge of kinematics. Okay, so that is the feature of JEE level questions, that the same question will involve knowledge of more than one chapter or more than one section. So here what is happening is we have an object like a spherical ball or something of mass m, which at t equal to 0, we have projected from the ground. Okay. At time t equal to 0, we have projected this from the ground with a certain speed, u equal to, let us say, 50 meters per second at an angle of theta is equal to, let's say, 53 degrees with the horizontal. And we'll take the value of acceleration due to gravity as 10 meters per second. Okay, so a body like a ball or something like that of mass m equal to 2 kilograms is projected from a horizontal surface as shown in the diagram at time t equal to 0. So that is when we are setting our stopwatch to 0 when we project this body. Now we want to calculate the work done by the gravitational force acting on it. Okay, so calculate the work done by gravitational force, that is nothing but the weight acting on it from t equal to 0 to t equal to 4 seconds. Okay, and then secondly from t equal to 0 to t equal to 8 seconds, and also from t equal to 0, sorry, t equal to 4 to t equal to 8 seconds. So in these three different intervals of time, every time we have to calculate the work done by the gravitational force or the work done by mg. Yeah, sorry, should be second square. Thanks for pointing that out. Oh, okay. So just use your knowledge of projectile motion over here to make sure you understand how you will calculate. As far as work done is concerned, the same formula will be applied. F dot S, where the force we are talking about is the weight. So it is mg acting vertically downwards. So the magnitude of the weight is nothing but 20 newtons and the direction is vertically downwards. But when you take the dot product with displacement, you have to calculate the displacement for each of those intervals by using this projectile motion concepts. Okay, so I'm not getting enough number of answers yet. Okay, just one or two people. Expecting all of you to be able to solve this by now. Okay, so let's look at this. So let's go back to projectile motion. So if you take this as your x and y axis now, horizontal and vertical, and the point of projection as your origin, then you can see that we can write our projection velocity in component form, something like this. So this projection velocity in component form, we can write it as u cos theta I cap plus u sin theta j cap. So in this, when you substitute u as 50 meters per second and theta is 53 degrees, you will get this to be 30 I cap plus 40 j cap in meters per second. Okay. And your acceleration is minus g j cap, so that is minus 10 j cap in meters per second square. So now when you divide the motion into the two components, now along x-axis what is happening, along y-axis what is happening. So your x component of velocity will remain constant. It will remain 30 because x component of acceleration is 0. So the x component of displacement will be 30t, u cos theta t. Along the y-axis, your velocity will become uy minus gt because your acceleration is minus g, minus 10. So this will become 40 minus 10t. And that is why your y component of displacement will become 40t minus 5t square as a function of time. So displacement at any particular time is nothing but xi cap plus yj cap. Okay. So if the projectile is moving in a path like this, okay, now it started from here at t equal to 0. So at any time t, when it's over here, the xy coordinates are given by these two equations, by this equation and this equation. So it's as simple as that really. Okay. So now you have to just implement this now for the given time. Just implement this for the given time now. So for example, in our first part, 0 to 4 seconds. So t equal to 0 पे उसके coordinates क्या थे? 0,0 थे. Okay. t equal to 4 seconds पे देख लो उसके coordinates कितने होंगे? Just substitute in this, you'll see. So this will be 120 and y will become how much? 40 into 4, so that's 160 minus 16 into 5, so that's 80. So this will become 80. Okay. So the displacement for this interval of time now, from 0 to 4 seconds, the displacement is going to be what? It is going to be 120 I cap plus 80 j cap. ये मेरा displacement हो जाएगा. And while this displacement is happening, the force acting on it, the gravitational force, is in which direction? It's vertically downwards always. So mg is minus 20 j cap in newtons because the mass was 2 kgs. Okay. And this is the displacement in meters. So the first part's answer will now come like this, that the work done for this interval of time work done by mg from 0 to 4 seconds, and we calculate this dot product, it's going to be minus 20 j cap dot product with 120 I cap plus 80 j cap. So that is going to be minus 1600 joules. Okay, this is going to be the work done. So this question is more really about projectile motion. Okay. The major part is the calculation of displacement using the component equations of projectile motion, and then the simple formula for work done. Now likewise calculate the next two parts. ठीक है ना? So understood this now. Now second part, calculate the this thing now, the displacement from use the same formula and calculate the displacement from 0 to 8 seconds. So you'll see something very interesting. 8 seconds is actually the time of flight. So it started from the origin. Now at 8 seconds it will be back to y equal to 0. Okay, it will become, if you do this calculation, just substitute 8 over here. So you'll get 240, which is exactly double of this x coordinate. But the y coordinate will become 8 into 40 minus 64 into 5, which will give you 0. Okay, so for this interval of time from 0 to 8 seconds, you can see that displacement is going to just be horizontal, 240 I cap. Okay, from 0 to 8 seconds. So the work done will come out to be 0. Because when you do the dot product, mg dot s, you'll see you'll get 0. So that's happening actually because of this. This is where the projectile is going to be at 8 seconds. And interestingly, 4 seconds was when it was at the highest point. Okay. So that is why, and all the while the gravitational force is constant, acting vertically downwards. So for that whole interval of time from 0 to 8 seconds, there is no vertical displacement. The net vertical displacement is 0. So the dot product with mg is coming out to be 0. Whereas third part, you can see when I'm seeing from 4 to 8 seconds, there's a downward displacement of 80 meters. This is 120 meters on this side, and this is again 120 meters on this side. So the horizontal range of the projectile is actually 240 meters, and the maximum height is 80 meters. The time of flight is 8 seconds. Okay. So now third part, when you see now from 4 seconds to 8 seconds, what is the displacement? Okay, so that is the displacement from this coordinate, which was 120,80 to this coordinate, which is 240,0. So the displacement is 120 I cap minus 80 j cap in meters. Okay. So the work done is going to come exactly is going to come exactly plus 1600 joules when you calculate by the dot product. And that is why when you connect this and this, now the total work done from 0 to 8 seconds is coming out to be 0. Because first, going from 0 to 4 seconds, gravity is doing negative work of 1600 joules, minus 1600. And then from 4 seconds to 8 seconds, the particle is descending, it's coming down in its projectile path. So now gravity is doing positive work. Because as it's coming down, gravity is also acting vertically downwards. So the work done will be positive quantity. So it will be exactly plus 1600. So that the net work done from 0 to 8 seconds, the full journey, that net work done should be 0 because there's no net vertical displacement. Okay, so people, is the calculation clear in this? Okay, hope you understood this. All right, now next we'll move to the second category of definition of work done. Okay, the first category was when we saw that the force acting is constant during the time or during the interval when we are calculating the work done by the force. But that's not always the case. Many times what happens is for the time interval in which we are calculating the calculating the work done, the force might be changing. Either its direction might be changing or its magnitude might be changing, or both magnitude and direction might be changing. So in that case, if the force itself is variable, then how do we calculate the work done? So that's the second part of the definition of work done. Let's look at that in detail. So work done by a variable force. So now imagine what is happening is a body or a block or whatever is going through some kind of a path like this from position A to position B. And while it is going through this path, the particular force that we are talking about, which is acting on it, that keeps changing. So when the body is here, let's say both the direction and magnitude of the force has changed. It's become like this. So the length of this arrow has also changed, supposedly, let's say. Okay. The direction has also changed, as you can see in the diagram. So when the block is at a position like this, let's say the force vector has become like this. By the time it's reached here, let's say the force vector has become like this. And somewhere here it is like this. So all the time the force is changing one way or the other. Okay. Then how do we calculate the work done by such a force? So what we do is, instead of calculating the work done from A to B straight away, we take a differential displacement or a very small amount of displacement. So let's say in a very small interval of time, the body is displacing from here to here, just this small. Okay. So for a differential displacement, the term differential means very small. ds. Okay, you can think of this as the displacement during a very small interval of time. dt. Okay. So during that small displacement or differential displacement, the work done will also be a small quantity, so we'll define it as dw. Okay, will become f dot ds, where f is the instantaneous value. Why instantaneous? Because overall the force is changing. So f over here, as you can see in the diagram, is a variable force. So point to point it is changing. It's a variable force acting on a body, okay, in motion from the point A to B, okay, through a path which is shown to you. Okay. So if I break this path into small little displacements, so for a very small displacement ds, now during that displacement, the instantaneous value of the force is, let's say, f. So f is the instantaneous value of the force during the displacement ds. Okay. So that is this quantity. So now the total work done as the body moves from A to B under the action of the force will just become the sum of the work done for each little part. So the net work done for the path or the entire journey from A to B, that will become nothing but integration of all these little small work done. So that will become, we can say it's equal to, now dw is f dot ds, so it becomes integration of f dot ds. It becomes integration of force with respect to displacement for the given path from initial position to final position. Okay. So in words, this quantity that we've written over here, the integration of f dot ds from initial to final, this is called path integration. Okay. So we say that work done by a variable force equals to the path integration of the force from initial position A, which I've shown in the diagram, to the final position B. So this is the general definition of work done when we are dealing with a variable force. So just make a note of this, people. Okay, so people, hope you have written down this definition. Now let's see how this is implemented. Okay. Now the simplest example of the implementation of this we'll see is the situation of work done by spring force. Because as you know, the force applied by a spring varies with the amount of extension or compression we are giving a spring. The spring force, you'll remember, is given by the formula Kx, and it acts opposite to x. If we compress the spring, it's in the direction in which the spring is coming back to natural length. If we extend the spring, it's in the direction. So if this is the natural length of the spring of spring constant K, so in comparison to this, if we give it a displacement x such that we are compressing it, so we give it a displacement such that we are compressing it, then the spring applies an outward force against whatever is used to compress the spring. Whatever external force we are using to compress it, this applies an equal and opposite outward force. Similarly, if we are extending the spring, such that this has become L plus X now. So the external force we have to apply to extend it is in this direction, but the spring's internal force, or the tension in the spring, or what we simply call the spring force, that will again be Kx in magnitude, but you can see it's opposite to the direction of the displacement. The displacement is towards the right, the spring is applying force towards the left. Yeah, so Hitanshu is fine. I will send you the recording later. We are just talking about work done by spring force. So you can pick it up from here. Okay. So now to calculate work done by spring force, because it's a variable force. Okay. So spring force is a variable force. Okay. Therefore, the definition of work done we have to use is path integration. Okay. So this definition has to be used. So as an example, let's see a situation where something like this is happening. We have attached a spring in between a wall on one side and a block on this side. So this spring of constant K is initially at the relaxed state. So this is the natural length of the spring. So initially the spring is in the relaxed state. Okay. So L is its natural length. Okay. Now what we are doing is we are applying some kind of pulling force on the block. Okay. Now an external agent pulls the block to displace it by a distance d, let's say. Okay. So in the next diagram, we will show that this same block we have displaced it in this direction by application of some kind of external force. So it has undergone a displacement compared to its previous position. It has undergone a displacement of move through a distance of d. Okay. So the spring has got stretched to L plus d by now. So we have to calculate the work done by the spring force. So given that the spring constant is, let us say, 100 Newton per centimeter, and the distance through which we are pulling this is, let's say, 5 centimeters. We want to calculate the work done by the spring force acting on the block for its displacement through that distance t is what we want to do. Okay. So this is what we'll have to implement to calculate this work. So just note down the situation first. We'll discuss about how to go about this. नहीं, मतलब d is the displacement ना. So see what is happening if this body is moving from this position to after some time to this position. Okay. So d is this now. This is the distance. The spring is extending by that. So that is the same as this distance. Okay. Or that is the same as the displacement of the center of mass. Understanding? So it doesn't matter whether we say it's the displacement of this edge or that edge of the center of mass. It's basically the amount by which the spring is extending up. Understood, na Hitanshu? Okay. So that's why see I have taken the front edge of the block in this diagram. Okay. But that is the same thing as the displacement of the back edge. You know, that's why the L plus D, that D is the same as this D over here. Okay. Now let's see calculation of this work done. So what is happening over here is that as the block is moving, the spring force is going to act in this direction, but it's going to be a variable force. Okay, and the displacement is in this direction. So that displacement we can call dx. So first thing we'll notice that the work done by the spring force will be negative. Why? Because the force is opposite to displacement. Okay. So that's one important thing. Okay. And secondly, we will have to use integration. Okay. Because the magnitude of the spring force is variable. In fact, it's an increasing force. As x increases, the extension of the spring. So we'll have to use integration. Okay. So let's see the implementation of this now. So let's say at some intermediate time, okay, in between the two initial and final, the extension of the spring is x. Okay, where x is greater than 0 but not yet equal to the total distance. Extension of the spring is the same as the displacement of the block. So at that instant, if you visualize the diagram, this is what it is looking like. Because the spring is in a state of extension, so the tension in the spring or the spring force acting on the block, that will be equal to kx in magnitude. Okay. Now imagine the block making a very small displacement from here. So from here it's making a very small displacement of dx. So while it is making that displacement dx, the force acting on it is like this. Okay. So from this state, for a small displacement dx, the work done by the spring force will be f dot ds. Okay. So that will be minus of kx into dx. Why it will become minus? Because the magnitude of the force is kx, the magnitude of the displacement is dx, but the angle between them is 180 degrees. So this information when you substitute, it becomes this. Okay. So now all we have to do is integrate this quantity from the initial position where x was 0 to the final position where x is d. So now the net work done by the spring, that will just become integration of this. So that is going to be integration of minus kx dx from initial position to final position. So minus k can come outside because it's a constant, x dx. Now the initial state is where x was 0 and the final state is where x has become d. So this will give us minus k into x square by 2 with the limits x equal to 0 to x equal to. So now just one more step and we can calculate the work done. Okay, so let's just go ahead and complete this calculation. Now everything is done. So work done by the spring, next step, is coming out to be minus half kd square. So we'll just substitute the values. Now k was given to us as 100 Newton per centimeter. So we'll convert this to SI unit. Okay, so it will become 10 raised power 4 in SI unit. Okay, and d was given to us as 5 centimeters. So that's 5 into 10 raised power minus 2 when we convert to meters. So this will now become minus half. K's value is 10 raised power 4 and D's value is 5 into 10 raised power minus 2 whole square. So as you can see, this will become minus 12.5 joules in SI unit. So this is the work done by the spring while we are pulling this block such that we are stretching the spring from its natural length position to an extension of 5 centimeters. Okay, people, so hope the calculation is clear. So we'll conclude today's session here, and next time we'll take it forward with more examples of work done by variable forces. And from there, we will develop the concept of the relationship between work and kinetic energy, and then generally speaking, the work and mechanical energy. So that's how we'll progress in this chapter. In the meantime, if anything pending in friction or Newton's laws of motion, please complete all that before the next session. Okay. And happy Sankranti to all of you again. That's it for today's session. Wish you all the best.